This is a conversation with Brett Aldrich, who is the CEO of Robosoft AI. Robosoft AI develops and maintains SMACC, which is a library that aims to make it easier for roboticists to control robot behavior. One of the key ideas in SMACC is that of finite state machines. We'll be referring to finite state machines a lot in this interview, so I'll explain what they are before we start. Imagine that you have a lawn mowing robot. Imagine that that robot is powered off and that you turn it on by pushing a button. It boots up and drives to a field to mow. When it gets to the field, it starts mowing. Once it finishes mowing, it drives home and powers off. This robot has states like powered off, booting up, driving, and mowing. The robot also has transitions that occur on events, such as when the robot is turned on by you pressing the power button, or the robot arrives at the grass to mow. These transitions change the robot from one state to another. For example, the event of arriving at the field to mow could transition the robot from the state of driving to mowing. So summarizing, a finite state machine is something made up of states, like driving and mowing, and transitions, when the robot has reached the destination or when it has finished mowing. This is the Sense Think Act podcast. I'm Audrow Nash. Thank you to our founding sponsor, Open Robotics. And now, here's my conversation with Brett Aldrich. Would you introduce yourself?
Yeah, my name is Brett Aldrich, and I'm the author of SMACC, State Machine Library for Robotic Applications written in C++. I'm also the founder of Robosoft AI. At Robosoft, we're the keepers of the SMACC toolchain. We're also the creators of the SMACC2 Runtime Analyzer. A graphical application lets you visualize your state machines both statically and at runtime.
Mm-hmm. And so can you start at a high level and explain what SMACC is and then what its motivation is?
Sure. SMACC is a state machine library for robotic applications. I like to describe it as dealing with the highest level of task planning and management on a robotic system. It has many unique features, and I'm screwing this one up. I'm sorry.
No worries.
Yeah.
Okay, so it's a high-level state machine library that helps you figure out, so you get to control your robotics application with it.
Exactly. It's a control. It's an architecture for control, and a couple of things about it. When you're writing your state machine, well, one, it provides a tight integration with ROS, allowing you to generate events for ROS topics, services, actions right out of the box. It also offers a reference library of state machines that are guaranteed to compile and run right out of the box.
So by reference library, you mean a bunch of state machines you can already use for specific things? Okay.
Exactly. With simulation included for many of them. So,
gotcha.
It also offers a client library, and this is part of the architecture of SMACC that allows ROS users to use ROS packages like move-it-to or nav-to right out of the box. And it also provides a pathway for other ROS packages and for the interfaces of those packages to be developed by specialists that are then tied to your state machine. All of these features have the effect of dramatically lowering the bar for new developers to get started in ROS and in programming in general, controlling their robot. I can go on quite a bit longer about this, but I would say that's a good high-level overview of what SMACC is.
Is it kind of so that if I'm using SMACC, I can kind of compose more complex behaviors out of almost like blocks that will affect their behavior, and I can I don't know, like if I have this sensor, I can use this block to send out the data, or is that how it looks? Kind of like a bunch of blocks that I can compose together?
Yes, yes, you have states, right, that you can use to divide your problems.
Hmm.
You have hierarchy, which does much the same thing. You also have the concepts of orthogonals, which are like boxes that allow you to modularize the physical subsystems on a robot.
Okay, and by that you mean kind of control them independently or use them basically, or can you give me a more an example, I suppose?
Yeah, absolutely. In fact, I'm gonna show a robot that was recently built using SMACC as an example. So this robot is from Fieldwork Robotics, and it was built by them along with ourselves in Bosch, India. And
It's
as you can see, there's 4 robot arms and a couple of trays, and a navigation base. So
looks like a fruit picking robot or something.
exactly, it picks
Okay.
raspberries. Yeah, and it was
So
based on the work of Dr. Sotens at the University of Plymouth in his soft robotics lab. So back
just to
to its
describe it
background.
for the audio listeners, it's kind of like a big moving cart with four different arms that's on wheels and probably drives through and picks stuff for. Would you say that's a good description of it, or
That's
anything
accurate.
to add?
Exactly, exactly. Um,
Okay, so you
and
use this.
so each orthogonal contains an arm. So there's
Hmm.
there's 4 orthogonals, one with each arm, another
Yeah.
orthogonal for the base. There's probably 2 more orthogonals for. There was like a packaging, not exactly sure what you'd call it, almost like a gantry, a small
Yep.
gantry inside for packaging the raspberries. Um, you probably also have your cameras with perception. All of these would go into an orthogonal. Using a model of, let's say, the human body, um, you might have orthogonal for your eyes, another 2 orthogonals for each arm,
Yep.
another orthogonal for
So
the head.
is it? Can you think of it kind of like a degree of freedom
Yes,
in a sense?
yeah, you can. Yeah,
Because so I mean, I'm thinking of so orthogonal, which means like it has a technical definition, which I think is it's the dot product is zero or something like this, right? So it basically means perpendicular, but it allows for higher dimensions, right? And so it's like a new dimension in state space kind of thing.
You know, the term that as I use it comes from Boost State Chart, and
Hmm.
it was always tied to physical subsystems. Um, and actually, from Boost State Chart, it inherited it originally from David Harrell's 1987 uh, paper on state charts. So uh, in 1987, David Harrell came up with state charts, and he developed that formalism, that I guess you'd call it an extension of the formalism of state machines, while working as a
Hmm.
consultant at Israeli aircraft industries, and in particular working on an avionics system. And so in that context of a fighter jet, each orthogonal basically was tied to a physical subsystem.
Hmm.
Yeah, as opposed to I think a more like a mathematical interpretation, which is where I think where you were going more with this.
Yes, that's where I know the word from. I haven't heard it this this state machine sense.
Mhm.
Okay. So then, so you have all these different orthogonals. I'm thinking of them kind of like a general degree of freedom, where multiple. So if you said a full arm is one, it's kind of like a subsystem, and then maybe you want to do things with it, and maybe that subsystem has several degrees of freedom, like a shoulder and an elbow and a wrist. But you're controlling it independently of other parts of the system. Is that kind of the core part? It's an orthogonal is something that is controlled independent of other parts of the system.
Yes,
Okay,
yes.
so I'm
Yep.
thinking generalized degree of freedom.
Hmm.
So multiple degrees of
Modularity,
freedom.
I think, is probably like more than a
Modularity.
degree. Yeah. Um,
Yep.
yep.
And can you have orthogonals in orthogonals? Like if I have an orthogonal that's my arm, can I have that broken down into orthogonals that are my shoulder, wrist, and elbow? Is that kind of this hierarchy?
Okay. So I think the short answer is no, in
Ah,
that the orthogonals can be quite complex, and so you definitely can have multi-joint,
Yep.
arms and
In
stuff.
one orthogonal.
Orthogonal. But one of the things that we did, we being Pablo and I, in terms of the
On this robot?
sorry, what?
Oh, sorry, I thought we were still talking about the robot for picking things.
Yeah, not for that robot in particular, but in SMACC as a library, and viewing SMACC in a historical context. One of the things that we did was we took the orthogonal concept that David Harrell and then Andreas Hubert-Dani put into instantiated it essentially in Boost State Chart, and we simplified. And because up until that point, so I think the world of Andreas Hubert-Dani, but he never really used the orthogonals, and the orthogonals in the context of a PC really don't make that much sense. And so we took them and began to use them, and we saw shortcomings with them, and so we simplified the orthogonal structure, and then what we did was we added this architecture part of clients and client behaviors. So inside of each orthogonal, so visualizing an orthogonal as a box, right? A box inside of a state box. There are generally two further boxes inside, that of a client and of a client behavior. The client has a lifetime of the entire state machine. So if you have something that some piece of code that you want to affect that robot in every state, then you just put it in the client. So this would be something like, let's say you've got a connection to a robot arm, and if at any time you lose that connection, you want some event to be thrown, you put that in the client. The client behavior, in contrast.
So it's like a global state in a sense.
Yeah, there is a globality to it. It's a different type of state, though, in that typically in SMACC, we're talking about states in a control sense. The states that are stored inside clients are more like an image state. This gets confusing, actually, in robotics. Like when you hear about something like state estimation, it's more like an image in a sense, right? And so that part is stored, whereas the control states are always explicitly controlled within SMACC, the state machine. But back to the orthogonals. So you've got clients that are scoped to the life of the state machine, and client behaviors that are only scoped to the life of that state. And you can have more than one client behavior at any one time. And I would say that that's where really the modularity comes in. That's basically how you interact with the orthogonals, is through the client behaviors. The client that sets up, let's say all the communication and all the kind of stuff that you want throughout the lifetime of the state machine, but the particular behaviors are in these modular client behaviors that.
So the client is like it's the manager of the So how do you call it? So you have the client, and the client is in a what was the word again?
Orthogonal.
So you have an orthogonal. So you have like a global state, and then from the global state you have your orthogonal. Your orthogonal is some piece that can be controlled independently of all of the other orthogonals. Yep. And then inside that orthogonal you have a client, and that client is going to control that orthogonal to run several different behaviors given the state. Am I understanding correctly, or not quite?
Both the client and the client behavior. But then
what's the client behavior?
The client behavior is different in that its lifetime is scoped only to that state.
And how are we talking about states in this? You were saying something about images and what is a state in this?
Yeah, we're talking taken from a control structure. So going back from like a global. The state machine is essentially synonymous with the application layer, right? So the state machine is your application. And there's one state machine on any one robot at any one time. Okay. Many libraries have like where you start nesting state machines inside of each other. We don't do that with SMACC.
You don't like it? Yeah. Okay.
I think it creates problems with data, with routing the data, and other problems. So you have a state machine that is your application. And within that
Mm-hmm.
state machine, you have a series of states, and they can be grouped in different levels of hierarchy. So
Mm-hmm.
um, let's
Like
say we
going
have.
back to that vegetable picking robot,
Mhm.
like that would be a nice concrete example to talk about this.
Okay,
Um, e-
okay, yeah, we'll use that, and also we'll blend in an example that I heard about for the DARPA Subterranean Challenge. So
sure.
in starting out, or in one of these teams that I had the pleasure of speaking with one of the people involved, they started out with a four-state machine. Okay, so four states. So in that example, you would have one state machine with four states. We'll
Oh,
ignore hierarchy at this point.
I see. I see one of my points of confusion. So
Mm.
state in robotics in like a control sense can mean like the thing that defines where the robot is. So this joint has this degree, this
Mhm.
angle, this joint has the next one. So I was trying to understand this, but you're using state as in a state machine. So it is a specific state that the state machine is in. And that's what we're talking about when we're saying state
Exactly.
in this.
Exactly.
Okay. So then we're saying we have a finite number of states. Those control basically the behaviors. Or we can do different behaviors in different states.
Correct.
And we
Correct.
move through from one state to another as the operation proceeds or
Yep.
something like this.
Based on
Okay.
events. Exactly.
I see an
And
ambiguity. Okay. That I was confused by.
yeah, it is. It's a confusing thing, and
So,
especially in
okay.
robotics. Yeah.
We'll just have to say states for state machines or something and states for controls or something. And that will
Yeah.
help keep me clear with it. Or I'll try to make it explicit anyways.
Yeah.
Okay. So you have your state.
So in this case, so back to this example, we had four states, right? So and we'll just name them state 1, 2, 3, and 4. So in each of these states, going back to the example of that fieldwork robotics robot, we would have, let's say, okay, we got one orthogonal for each arm, one for a base, one for the two gantries. So that's 4, 6, 7, and let's say one for perception, 8. Okay, so in each of those four states, you're going to see 8 orthogonals that
Okay.
inside, each one will have a
Ah,
client in every state. And then depending on what behaviors we want that robot to express, we arrange the client behaviors accordingly. And so it provides like a modular control structure for each subsystem of the robot.
gotcha. So
And the
you
state,
are, yeah.
and the state basically serves as like this gets more into like the substate architecture of SMACC, but the client behaviors and the clients throw events based on what happens outside, so SMACC is a single node. Back to this example, SMACC is a single process operating at runtime, and you're also going to have, other processes on this system. You're going to probably have nav2. You're going to have move it,
Mm-hmm.
one with perception. And so when those other nodes communicate via, let's say, ROS topics or services, the SMACC clients will turn those messages, which you'll specify, into events. And then those events
Oh,
are
that's cool.
coordinated by the state, like a conductor would,
I
And
see.
so on this event, we transition to this state. At the end of the day, states are a lot of people. You might in coming to state machines, you might think that that state machines are about states, and they're really not. They're about events, and
Okay.
it's through events that you begin the subject of states almost. It's like it begs the question. Like when you have an event, you have what was before and what's after, right? And
Can you define an event for
sorry,
me?
what?
Can you define event?
An event is, they have general explanations. It's like some type of discrete.
So in ROS, it would be, have I received this message or not?
Sure,
Is
exactly.
so the event is the message occurring. This kind of
Yeah,
thing.
exactly, exactly. Or
Could
the
it be
action completing, or
so? Oh, or the action completing, or something like this. So if I'm using nav2 and I want to move from one spot to another spot,
Mhm.
the action completing of me moving to the location could be the event.
The
So it
event.
says, I'm in this location, event has occurred, kind of
Event has
thing.
occurred, and then when that event has occurred
You do
in
something.
SMACC, in a state, yeah, you specify often where you will, like what the next state you'll transition to is. And
So are we always transitioning on events, or so do you always go to another state, or you can probably stay in the same state and have several events? I'm just trying to think of more complex behavior.
Yeah.
But so are events always used? They're not always used for transitions, but they...
Not always, but and here we get into the minute you start using events, you start using more. Another one of the features we added to I'm saying these are things that I think are interesting historically in the sense of like what's unique about SMACC, versus let's say Boost State Chart and what happened before. We brought in the concept of state reactors.
Let's define a few things, just because there's a few things that I don't quite understand before we get into state reactors.
Sure.
So I don't quite understand the difference between clients and client behaviors.
Sure. It comes down to their lifetime. Clients are lifetime to the state machine. And client behaviors have a lifetime specific to that event.
Oh, okay.
So
client behaviors are just for behaviors, or how does it? Why are they named that? Let me just see. I think my smoke alarm is going, or some smoke alarm.
Oh, it does sound like a smoke alarm.
I do hear a beep beep. I'll probably just filter it out in the thing, so long as I don't smell smoke and whatever.
Yeah.
Okay.
If you do, get out of there, man.
Yeah, for sure. Yeah.
This gets into like the systematic architecture of code layout that SMACC offers. So let's say you have something that you want that robot to do, like some type of event that you want to respond to in a particular way, but you want that to be throughout every state of the state machine. You'd put that code in the client.
I see. Yeah. Okay, so you generate these client behaviors when the event happens, and that will take care of a specific, they're kind of created and destroyed on a specific event, whereas the other one occurs all the time. I'm thinking of them like kind of simple, but for like web pages or something, like you always want to load this one thing. It's going to happen no matter what page you do. So it's like the header or something of it that's always going to be the same. And then your client behaviors would be the very specific things that are on a specific route in this case.
Yep.
Is that a fair way to think about it?
Okay. No, it's very good. And the only nitpicking thing I would have there is that they're not so much, the client behaviors aren't created with events, they're created with new states. So when you transition from one state to another, that's when the client behavior is created at runtime.
Okay, I see. Okay. And then so there was another thing that you were going to introduce.
Yeah, state reactors. So this is another type of, this is all part of the sub-state architecture. So like once we're in a state and looking down at the pieces inside of it, what state reactors do is
so in the sub-state, what composes a sub-state? Is there states within states, or are there?
Okay, so we do have hierarchy. But when we're talking about in the hierarchy, one thing that is unique in SMACC, or maybe I don't know what's one feature. We break down the library into having container states and leaf states, and it's the leaf state that has the orthogonals and the full substate architecture. The container states don't by default. You can turn them on. At SMACC, we've followed a philosophy of we do things in a certain implementation that, as we see, that we think is best, but we try not to turn off like other ways of doing things because some of the early clients that we had really challenged my views of how they would interact with the system. And I'm thinking of you, Bob Peath at Gray Orange. Um, they did things that I was like, what are you doing? You know, it took me back, but a totally valid way of running things. So we try to leave those sort of things open. But anyway, back to the hierarchy. So generally, there's always a leaf state that has orthogonals and other things like that. A state reactor is just another one of these objects, and what it does is it receives events and throws its own event, and so it basically brings in second order events. The first use case, so we came up with it. This is in like mid 2018, and we'd just begun the library in like at the end of 2017, and we were contacted by the company here.com, and they were working on a self-driving car at the time that it had a very complicated array of 6 like super high-end cameras. It was for like a self-driving car that would map, you know, as well. And what they wanted it to do was, you know, navigate from one point to another. When it started up, it wanted to make sure all the cameras were ready to go, and then drive. If anything happened, stop, bring all the other cameras back online, and go. And that led me to create the state reactors. And so what we did is we have a state reactor called All Events Go. And it's a runtime object that resides inside the state. And it receives events from camera 1 event, camera 2 event. And once it's received it from all, then it throws its own event, and then the state transitions. It's become such a popular, I'd almost say it's a state machine design pattern. You know, we call it ST acquire sensors, and I don't know what percentage of state. You know, we have in the reference library we have certain state machines that are extremely simple. It's just like one stick going back and forth, so they don't have it. But I think for all of the other state machines that we've, like if there's a simulation video, I'm pretty sure all of them have one of these ST acquire sensor states very early on in the execution of that state machine.
Gotcha. Okay, so you have those that will kind of take information and they take in all the events, and then when a specific condition is met, they may emit another event, and that can be used to trigger some sort of transition or whatever might occur.
Correct.
Okay.
They also, one other thing too about them that's, I don't know, that might be interesting for the specialist out there. They've set the stage for us to move ahead with code generation in a new way. One of the things that's always plagued state machine libraries when you try to
boilerplate code, or
yeah, well, boilerplate, but also like graphical code generation. That one of the problems that it has always complicated that is callback functions. But with state reactors, you avoid that through these second order events. And so and that's part of our plans over the long run, you know, to build out an entire tool chain along with the ability to right now we have the SMACC2 runtime analyzer, but we want to create a SMACC2 writer where you can, you know, graphically align your state machine and have it auto generate the code, or at least generate some of the code, you know, like a lattice framework type of thing. And yeah, the only thing about that is that in my opinion, you have to do that last, because if you do that too early and you've got some problems in your, you know, in your architecture, you basically baked it in place. So
I see.
Yeah, so that's one of the things I'm really hoping to accomplish with SMACC in this current year is basically getting more and more use cases to a point where it's like, okay, no, we've seen, you know, we've got an idea about every which way that the library could conceivably be used. You know, I don't know if we'll actually get all the way there, but
if you get a lot of them, then you have a fairly general solution, and then it can be used for a lot of things. That'll be great.
Yeah.
So one thing that I don't quite understand, well, I guess I'm having trouble mapping the ideas together. So I understand this architecture with the client behaviors, and you have your orthogonals and you have your states and things like this.
Mm-hmm.
Can you explain kind of, so like a simple application, say like that video of the fetch sorting, the fetch in simulation sorting cubes by color?
Okay.
Like how do we go from these states and then the orthogonals in them, and then how just like an idea of how all the systems work together to create some reasonably complex behavior?
Hmm. Hmm.
Or it can be a simpler one if that's kind of complex.
Yeah, maybe we'll start with the dance bot example. We'll kind of dive into that one a little bit.
All right.
Sure. In so for those who who haven't seen it, the best spot to see the dance bot example.
I can link it.
Yeah, is in the Ross World 2021 presentation on SMACC2. It's the opening video. How we link that all together?
And just to describe the video a bit, it's a robot that it's in a sort of maze, and it goes to a location, and then it drives until it hits a wall, and then it goes back to its original location, and then it goes out again, but slightly different angle from where it was heading. Mm-hmm. So it makes kind of like a star pattern, and where it goes and it bumps each of the walls around it, and then it goes back to its original location, and then it goes to some other location to start doing the same pattern there. And I believe the intention with this is to map out an environment.
Not exactly. It's I mean, there is a mapping that does happen, but it's really more about floor coverage. We were modeling, how a robot might cover a floor space in modular ways. So in that one, the robot navigates to global waypoints, and then proceeds to perform. It enters a super state. So now we get into hierarchy a little bit. So we've got our leaf states. And then you can have these container states that are like levels of hierarchy, which we have shorthand for, which I'll go into right now. So the first level of hierarchy we refer to as super states. The next level we refer to as mode states. There's no difference per se.
But it's just because it's a hierarchy. So the super states is like high level control, and that's like fundamentally what the robot is doing. It's mapping, it's driving to some location.
Depending on how you organize your application, yep. I think the most common use for super states is for loops, or like sequences, So in that application, it moves to the first global waypoint. It proceeds to execute a super state that is a radial pattern, and you can set the parameters of that radial pattern in the super state. So I think in the video it showed something like 16 rays. And
so 360 divided by 16, and then it just went out
exactly
at each of those angles. Okay.
But you would just go in there and let's say put in 32, and you'd get,
so it's parameterized.
Exactly. It does 3 of those super states in a row, at which point it navigates to a fourth waypoint, and we have it execute an F pattern. Same kind of thing, although it's like, I think it's a series of 7 states that execute this repetitive F pattern. Again, though, designed for floor coverage. Then it goes to a final waypoint where it's more of an S-shaped pattern. So 5 total super states. And 5 global waypoints. All the super states parameterized. In this case, we're only using 2 well, let me think. There might be more than 1 orthogonal in there, but in terms of like the crucial orthogonals for that example, there's 2. There's the LiDAR and the NAV2.
Cool.
In that particular example.
And NAV2 handling the navigation of the robot from one spot to another.
Exactly.
And controlling the motors and everything to drive it around.
Exactly.
Right?
Exactly. Yep. In other state machines, we might use something like ROS2 control, in the same, in kind of a similar
Yep.
way that move, it relies on ROS2 control to move the robot. And we've built examples in navigation in ROS1 where it uses the ROS2 or the ROS control diff drive controller. But yeah, it's, you start using like your standard ROS stack to
Okay.
navigate around. Yep.
And then so if we're in super state 1, we're in the radial star
Okay.
1. What does that look like from the mode states? So not the super states, but now we're in super state 1. And so super state 1 is composed of mode states, as you were saying with the shorthand.
Yeah.
So how does it look there? Like what's going on down there, and how do we get closer to
I'd have to
the
review
clients?
that example like in depth,
Or
but
just
I believe,
ballpark?
yeah, I believe the way it has is that we've got a mode state called run, and we have
Mm-hmm.
another one called recover.
Mm-hmm.
And where I see that architecture evolving and going, in terms of real world, is that one of the things that SMACC offers is very advanced recovery sequences and capabilities. So I imagine, and I think one of the things that SMACC, one of the most important things that SMACC offers in why it's disruptive, is that it allows for a new order of magnitude in the complexity of robotic missions, particularly multi-stage missions. So for instance, let's take an example of a fixed wing aircraft, right? So you'd have one mode for taxiing on the runway, another mode for takeoff, another mode for, I don't know, your initial flight where you're finding your right heading, stuff like that. And for each one of those modes, you're probably going to want to have a separate recovery state, or a separate recovery mode state, where so let's say you're in takeoff, right? And something wrong happens, then you switch from that mode
to the appropriate recovery for that.
Yeah, mode takeoff recovery, and you begin your error recovery procedures there. And as that continues to expand, you end up with like greater needs of hierarchy. It also brings in the question of where your data goes. Another unique feature of SMACC is that every state is a class and every container is a class. So you can scope your variables and other things to the lifetime that's needed. Perhaps you need a variable across every state in a certain mode. Perfect, you put it in the mode. You can also do, we also have the option of global variables, but
yeah, okay. So interesting. And so can you tell me a bit more about the real, so you were saying, I guess the origins of SMACC and how it was born from, I guess, a real application, and then how it's evolved since.
Yeah, it's, the origins of SMACC, it's hard for me to put a finger on it. I would say it started, let's see. So I graduated from UCLA with a degree in biochemistry, and one of my first job outside of university was under a NASA grant at the UCLA Medical Center in the Department of Head and Neck Surgery under a brilliant researcher named Dr. Larry Hoffman, and I ran one of the research labs there. I forget my exact title, but one of the labs was basically mine. And what we were doing was, it was this insane program where we were dissecting the inner ears of, we were injecting like dyes and then dissecting the inner ears of mammals, mainly chinchillas and mice. And then we were studying the organelles of the inner ear, the utricle and the saccule and stuff like this.
I don't know anything about this. Okay.
It's an arcane
the little parts of the
subject, even then. And in dissecting these organelles, we would then visualize them, under fluorescent microscopes. And imagine like I'm holding up for the listening audience. I'm holding up like my hand. It's like an organelle, and it's like they would have these nerve patterns that would kind of follow through these organelles, and we were studying those in an effort to create better rocket guidance systems, which I have no idea if it ever resulted in you
Huh.
know such things. I have a feeling gyroscopes do a pretty good job, but it got me. It brought up
So it
all these.
was this was like fundamental. So like one thing that might be similar is I think it's rapid random exploring trees, RRT or something like this. I probably
Yeah,
have to.
yeah,
So
okay,
it's almost like you're trying to identify an algorithm that controls these nerves spreading through them, and then maybe that algorithm would be useful in applications like guiding missiles or whatever it might have been.
yep, that's exactly right. Um,
Okay.
and that's and so it opened, exposed me to concepts like this. Neural nets was talked about. Um, I got to program a little bit of Fortran. Also, decision trees were part of that, and it 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 began an interest that I had, like even in terms of off hours, where I just started. I started sketching out these kind of systems, like, and then in looking back on it, it was clear to me that I was drawing out state machines. Although my earliest state machines, it's like each state was a neuron, and so I was imagining these chains of neurons and how they would process information, and what where that would go.
Interesting.
Yeah.
Yeah.
Um, and so anyway, that was where like some of my earliest interest in that arose. Later, I went back to school to get a degree in math and theoretical computer science at the University of Irvine, and
Hmm.
which I did not complete. But in some of the early courses, I was exposed to set theory, automata theory, and so I
I
was
don't have
exposed
any
to,
idea what that latter one is.
automata
Automata
theory.
theory?
That's like the math behind things like finite state machines.
Huh.
Uh,
Okay.
yeah, you get there into like whether or not state machines are Turing complete, stuff like
Ah,
that.
so you're
Um,
proving things about them theoretically, in
yeah,
a sense.
exactly.
I see.
Particularly when you start getting into advanced state machines with event queues, and like how that
Hmm.
how that maps. Um, so there was that part as well. Um, I uh, Moving on later, I remember there was when I started believing that robotics was the next wave, um, that it was, and I believe this still,
Hmm.
that robotics is going to be the next boom and probably the biggest one in my lifetime. Um,
Hmm.
I feel like that's going to happen too within the next 10 years. And so as I was looking forward to that, there was a book called UML of Real-Time Systems, and I read that book. Like I've gotten rid of it since, but I don't know. I could almost probably tell you on a particular page what's on it. And I did a
Wow.
lot of sketching too. At that time, though, although I was so interested in them, I never would have thought that I could have written a state machine library like that. I would have thought that, well, and at this time, this is really before ROS, so like the systems were more closed off. I would have thought that was,
Ah,
be part of some giant proprietary stack.
I
Um,
see.
yeah. Anyway, my first project, that involved ROS was creating. Well, so the company was Real Robotics, and we were creating level wind cable reels that were going to provide mobile robots with tethered AC power for,
What'd you what'd you
more,
say?
sorry,
Level line? What'd you say?
level
What kind of
wind.
key?
It's a level wind, meaning
Level wind.
level
Okay.
wind, meaning that if we've got a reel here and
Goes.
you've
It's
got
like a fishing.
exactly like a fishing
Like a
one, so
fish.
yeah, there's like it goes like this, so it winds perfectly
Yep.
every time. Um,
Cool.
and I've got a picture too of like what we had in mind for the system. I'm holding it up for the camera right now, and it's on top of a ClearPath Robotics Ridgeback
Oh,
robot.
okay. So,
And you can see the box that is the reel. There's a yellow, it's meant to be a like a 9-gallon shop vac that goes on top in this application. Here, I'll show it from another angle.
huh,
That's the system.
okay. So
And
it just looks like so it looks like one of those small clear path, or maybe not small, one of those clear path robots that has kind of the wheels underneath, and then there's a big cube on top of it, and it kind of looks like there's, so I guess that's the shop vac cylinder that sticks out of the cube.
yeah, exactly, exactly.
Okay.
Um, and that's
So you started with this. So the problem was to do level cabling. So you wanted to basically have the robot drive and it would leave a cable behind it.
correct.
And then you could wind back on the same path and it would
Yeah,
organize that cable as it retracted it, basically.
exactly. Which
Okay.
required tight coordination with navigation,
Hmm.
and then also tight coordination with what would be really the state machine of whatever, the plan was to basically sell those to OEMs, and so we knew that
And the
we were
OEM is original equipment manufacturers,
exactly.
right?
So let's say
And so that's
somebody,
like, yeah, go ahead.
well, yeah, somebody like Dyson vacuum or something,
Okay.
probably more industrial, something like Tennant or Nafilsk, but yeah, whoever was going to
Okay. I
make
don't
like
know them, but I see.
yeah. And so we knew that we were going to, so we built, we started with that software stack and we moved all the way up. And we really did some beautiful work there. Some notable people too contributed on that project. Dave Coleman wrote some of the code on
Oh,
that project. Yep, yep. I
hell yeah.
recruited
For
Dave.
picnic.
This was before Picnic. He was a graduate student at University of Colorado Boulder, and he wrote some of the original ROS control code. Um, Vince Magyar also worked on the project. He's the maintainer of ROS2 control.
Hmm.
A mathematician by the name of Rob Hanna from UCLA and I we mapped out all the mathematics where, imagine that level wind system, the goal is to know exactly how much cord is being produced with every encoder tick, but it's changing all the time depending on how many layers of cord are on the reel,
Yeah.
what's the position of the level wind carriage, where the robot rotating, and so we did all that. I focused on the microcontroller code mainly, and that's kind of how that was more my background as I came into SMACC. I was more like an embedded programmer. And
Hmm.
at that time, I thought that C99
That's
perfection.
where it's at. Yeah.
That was my belief. And anything involving templates, I looked at like, I didn't like that at all.
Yeah.
Pablo contributed
Uh,
on the project too, and there was also a developer from the former ClearPath developer named Devin Ash who did some really great work on the project too. Um, anyway,
it's
we
cool to
knew,
see. It's funny to me that it's such a small community in a sense, as in these names keep popping up for a lot of endeavors.
yeah,
Okay.
yeah,
So you worked on this robot,
yeah.
and so this was with real robotics, and this
Mhm.
was the application.
Yep. And we
And so
knew
SMACC was born from this?
correct. Yeah, because we knew that we were going to have to integrate with whatever the OEMs were using for their top level coordination, because you have to coordinate. You'd have to coordinate the movements of the reel with the navigation, the navigation of the robot,
Yep.
which we accepted. We knew we were going to have to do custom work like that, but
Hmm.
in order to develop our own demos, the idea of a state machine came in. Also, early on, I'm going to say, so we started this in like 2015, 2014, 2015. By 2016, maybe even a little earlier, I realized that Smash was not up to the task.
And Smash, what's Smash? Is that a
Smash,
former?
oh yeah, Smash was the state machine library developed by Jonathan Bullrun, I believe in 2009, and it was the
Okay.
state machine that powered the PR2 examples.
Oh,
Um, yeah, I think very highly of that library. I think he did a number of very, very innovative things that that inspired SMACC. Probably the most important was tying the events to actions. So like in the example you were describing too, when navigation finally gets to a goal, that that then creates an event and you transition to the next state. Exactly. There were things though about Smash that never fully. So I want to give credit to Jonathan Boren, like for like it was a creative and in that sense a leap forward. I think in terms of though like it was never really suitable for like more of a production level of robotics. The concurrency always had issues. The data porting is another subtle problem. Anytime you see, in my opinion, anytime you see data porting in state machines, run.
I don't know what data porting is.
Well, it's in Smash when you wanted to provide hierarchy, right? It was you would put another Smash state machine inside of a state machine.
Oh,
it was like, yeah, it was like you had that,
and then you would forward state down or something, or
well, yes, this is where it starts to get interesting, and how you move data around. It's a design pattern that's very common amongst state machine libraries where people try to do that. I think it's fraught with problems, and usually in where you're trying to move data around, and where you have to be explicit about where it goes, that doesn't really scale. But anyway, so late 2015 or mid 2015, I'm looking at Smash and I know that it won't be the library that allows us to, we can't use that one. And so I looked at the market and I didn't see any competitors, and I saw a chance, where we could take a stab on writing our own. I knew it was a daunting prospect, but I don't know. I take risks every now and then, and I think I fell in love with the idea. I think because if I try to justify it in terms of cold hard business logic, it's sort of tough. But we set out that way, and I started on it, architecting out what that solution would be, how I would piece that thing together, and I settled on Boost State Chart. Mainly, one thing that helped me in that stage was that I focused solely on the needs of the robotics.
It's a C++ library. Boost what?
Yeah, exactly. And it's template metaprogramming based, which is
what's it called again? The library?
Boost State Chart.
Sharp?
State Chart.
Chart. Ah, okay.
Chart. Exactly. And that comes from David Harrell named his models of state machines state charts. So it comes from that.
Yeah. It's an arm to it. Great.
And yeah, so we started that we started coding it in approximately 2017, or at the end of 2017, excuse me. But I had been working on it for about a year at that point, just like laying out the architecture. I used my intuition largely, but I got pretty good intuition. And later, as I learned more, I look back and I'm surprised how many of the decisions we got right.
Nice.
Yeah.
Okay. And so then real robotics closed down, or
no?
Was this?
Yeah. So,
what
exactly? In 2017 we began. No, I'm sorry. At the end of 2017, we began building the library, and very, very early, the market pull started to pull us in. So that call with here.com, that took place, I think, in May of 2018. So it was as soon as we were developing it, we started getting calls. Then we started working with Gray Orange. I'm going to say late 2018. So we started just being pulled into one meeting after another. and then two, I picked up confidence as we proceeded.
Yep.
We then ran into so at that point we were developing both Real Robotics and SMACC, which later we split off into Robosoft. But at the same time, we were pursuing them at the same time. That went all the way up until we announced the library in 2020. In June of 2020, we announced SMACC.
Oh, wow. Okay.
Yeah. And we set out one to finish up the reel, and our plan was to launch them together. And it worked.
Launch the reel, launched what together?
Launch Real and SMACC together.
Launch the company, Real Robotics, and
and
SMACC at the same time. I see.
Right. Yep. And we ran into a mechanical issue along the way. So we announced SMACC for ROS 1 in June, and we immediately set out to create it for ROS 2, because I realized that as we announced the library that that at that point most of the major players were already moving into ROS 2, and so we immediately set out another version, and also set out to complete the reel. And where it's at now, the reel works. I've got a picture too of it. Like we built this thing. It's awesome, and there's one mechanical issue, and but the market pull was just too great, and so I'm putting it down for a while and putting all of my focus on SMACC now.
So
I
you
think
mean
SMACC's a bigger idea, you know?
So
I think,
by market pull, you're meaning that there was so much customer demand that it kind of sucked you away from Real Robotics.
Yep.
Sucked the time and energy. Okay.
Yep.
So then,
really
what do you think? So, what is the appeal of SMACC to these companies? Why are they, like, what are they looking for that SMACC is meeting? Like, and why does it not? Why are there not alternatives? And I don't know why is SMACC so appealing to them? Basically,
I think the first part is that you've got a standardization at the application development layer. You know, SMACC can be viewed as basically an application development framework. So I think that's what draws them. I think the features of SMACC then start to come into play, and I'll try to go through a few important ones. One of which is that being a with SMACC, you can build state machines that are an order of magnitude more complicated than with almost any other library. The reason for this is the compile time validation. This comes from Boost State Chart. So I don't know, have you ever heard of the n times n problem in state machines?
I don't know what it is in state machines. So
it's, you know, it
becomes intractable though.
That when you have n states, right, then you might need
and transitions.
So many transitions, to each state. And so it just gets bigger and bigger. You know, like if you've only got 5 states, okay, great, you got n times n is 25. But what happens when you have 20 states, 30 states? Yeah, that expansion. And this, I feel like the academic treatment of the n times n problem is overly simplistic and misguided. But there is
it might be just more theoretical, and it might miss some of the application, considerations and application.
It's true. And I also think it's somewhat sloppy. It seems like big O notation, but without the rigor, I'd say. But anyway, it is true that the larger your state machine gets, the harder it is to manage that, or at least it can be. And this also gets into one criticism of state machines, is that they're a one-way transfer of control, right? Like, so when you go from one state to another, you don't automatically go back to the state you were in currently. And in that sense, they've been compared to go-to statements.
Okay, so you just jump around.
Where you jump around. And while I think that's a bit of a stretch, there's a truth that if you go to the wrong place, then you're in big trouble, right? If you're transitioning to a state and there is no state there, we got undefined
Yeah,
behavior,
undefined. Yep.
right? But what happened there is so template metaprogramming arose
What
in
does
like
that
the late,
what does that mean?
yeah. So
So I'm familiar with templating in C++. Is it anything similar?
it's very similar. It's the same type of.
And metaprogramming, is it like Lisp? Like programming with
I don't know
macros
enough
in
about
Lisp?
Lisp
Oh,
to
because
control.
that's what.
But
Okay,
what
because
it
that's
does,
a beautiful thing.
it happens
But
at compile time. That's the key
hmm
thing, is that template metaprogramming by occurring at the compile time, uh, that's what sets it apart. And
because you can have all sorts of compiler checks rather than runtime checks or this
exactly,
kind of thing.
no, that's it.
So okay,
That's
so
it.
because of that, you just run and say compile and build and whatever, and it's going to go and it's going to suss out a bunch of problems for you rather than you having to like test them.
Exactly.
It, I see. So
Exactly.
it's much faster and easier for the developer in this
That's
sense.
right. That's right. Much safer. That's right.
So
Um,
can I take a stab at what template metaprogramming would mean? Because I'm imagining it similar to what they do in Lisp, and I'm imagining it somewhat similar to what they do in C++. So it would be that you're writing code, and your code at compile time is going to like expand things, run them through functions, and then it will change what that function does based on arguments or this kind of thing.
okay, that's more like function templates. Yeah, but it's
Oh,
same
okay,
same thing, right?
same
Or
kind of
how do
thing.
I say that? In let's say if you were starting to look into like the template metaprogramming that works in Boost State Chart, that would be like the opening chapter. You'd start
Okay.
there with your function templates,
Yeah.
but then it moves into class templates and
Okay. Well,
yeah.
yeah, so you can do all sorts of objects this way. I mean, you
Mhm.
could do functions, you could do classes, but it's fundamentally the same kind of approach where
Yes,
things are parameterized and it's generating stuff based on those parameters by
type.
following,
Yeah,
yeah, by
yeah,
following a code path that you define, which is the meta template programming part of it, right?
yep. That's right.
Something
That's
like
right.
that?
Yep, that's
Okay.
right. And in the like in 1995, there was a famous paper by James Copeland where this pattern called CRTP, and it stands for the Curiously Recurring Template Pattern, was discovered. And it was discovered by independently by a few, but one of them was a female programmer by the name of Lorraine Jewell. And it's that method was then taken by the developers of the Boost libraries. And a lot of people don't know this about the Boost libraries, but the Boost libraries are all based on template metaprogramming.
Huh.
David Abrams was the founder of the Boost libraries, and he wrote a library called MPL. It's a metaprogramming, I think, metaprogramming library. And then two important state machine libraries emerged from that early period. So Boost was founded in 2000, and two libraries, Boost MSM, which was written by Christoph Henry, and then Boost StateChart, which was written by Andreas Schuberdani. And both of
Hmm.
them use CRTP to validate the state machines at compile time. And in Andreas Schuberdani's implementation specifically, it's a game changer because it makes sure that every transition has a source and destination. It makes sure that every
Hmm.
state has a parent and a state machine that it accounts for.
So you get a
And
lot of compile time safety, basically, because of
yes,
these validations. Okay.
yes, and I think too you get it's one saying I've got is that it's very easy to write a state machine library. The trick is making one that works, and uh,
Mm.
and the fact that it's compiling every time you're compiling, you're getting checked. It just has a different type of reliability, a different type
Hmm.
of reusability, and it's tied to that. Um,
Okay.
yeah, and
So,
hence why I think where you're able to, and that in combination with state local storage, um, is what allows Boost State Chart and through inheritance SMACC to have state machines that are orders of magnitude larger than what you would think if you believed in the n times n program. For instance, in the SMACC2 repo today, there is a state machine known as SM Multistage 1. I wrote the state machine. It has over 165 states and over 100 transitions.
Wow.
You know what I mean? It's not that big a deal. Yeah, like it wasn't that hard to write. It didn't take that long. And if you mess up anything, you know about it at compile time.
Yeah, that's really nice.
Yeah.
Okay. So you mentioned all this industry interest in, or you mentioned all this interest in SMACC. Can you tell me some of the types of projects that you've been working on with it, or some of the types of companies or the problem domains that the companies are interested in solving with SMACC?
I'm trying to think of like patterns across them. I think the main one that has brought them at this stage, you know, to SMACC is the problem of concurrency. You know, basically, how do you control, and you know, I think we would start with navigation and at least one arm and maybe two, and then a perception system and maybe a gripper. You know, like just some type of minimal implementation like that. Although, as we saw in the fieldwork robotics example, you know, it quickly went to 4. Other ones, let's see.
What kind of domains or tasks are they trying to solve? Like what does a task that you can accomplish look like with this, I suppose?
Yeah. One was like a self-driving car. Another, it's broad. It's broad in that. Another one was with gray orange. Theirs was it was a two-armed. It was a robot with 2 arms on a gantry that was in like a warehouse type context, and I believe it was used for folding shirts.
Cool.
Yeah. So, but again, we have multiple orthogonals, right? Like multiple, you know, arms in one application. And then for fieldwork robotics, you know, again, like then we have the expansion to multiple arms. I would say that that's probably at this stage the most important element is the modularity that comes with orthogonality. Areas that I don't think have been touched yet with SMACC is the complexity that it can go to with multi-stage missions. I'm not sure.
So where would that go? What would be some problems that you could solve that are kind of like pushing it to its limits in complexity?
Well, let's see. Let's see if I can think of a.
Would it be like space-related things? Or...
Okay, yeah. I'll try to freestyle a space-related mission. You know, one thing I've heard being talked about at DARPA is where you can really bring down the cost of launches, right? Where let's say you've got like some type of launch, like some. Say it's like a truck type device, but it navigates out to somewhere on its own, sets up a launch pad, and then launches into space, right? It's almost like a transformer in that sense, you know? So you could have one mode state that's for your driving portion. And you're going to need different recovery procedures, you know, depending on
the whole driving, everything. Yeah.
Then you transition to the launch area setup state, and you know you're going to have multiple sequences involved there, different recovery procedures, et cetera, et cetera. Finally, the launch, and you know again it changes, and in fact, your orthogonals would change, right? Probably like the physical subsystems that you care about in each one of those contexts would be modified.
That's a cool concept. It does make sense.
Yeah. And then too, you know, if that truck's got to get out of there afterwards, what if it has to, you know, it wants to launch and move? So that would be another another word where you just keep chaining on and on. And I do foresee one bit of feedback that we've gotten that I think is important is that as people start to use events in their programming, you start having an explosion of events, which is good, but you just want to handle them more. And once you start using states to chop up your problems, you want more of them. I think that's another interesting thing that SMACC does is if we look at it almost from economic terms, it dramatically lowers the costs of creating states. Like for instance, one of the examples that I think is sort of striking is, the early 2004 DARPA challenges, right, where you're navigating across the desert, and I feel that still influences navigation, like even to today. These A-star planners and stuff like that make these very complicated, plans. It's almost
and so just a little background. So A-star is kind of an optimal planning algorithm that'll go, and it has a heuristic for how it proceeds, but it goes, the goal is that way. I'm going to explore everything towards that direction. And when it arrives at a solution, it computes the optimal solution in the environment. So that's why it has the star. But okay, so when you're doing path planning and you're using something that can get an optimal solution, this is as compared to like RRT, the rapid random exploring trees or whatever it is, which finds an approximate solution by kind of branching. It's not optimal.
And it samples off of it.
Yep.
Yeah.
I mean, you can use that and then optimize from the RRT one. But okay, so you're saying A-star for exploration and...
Well, it sort of has, in my mind, the assumption that there's only one state, that you've got to navigate from here to Vegas in one state. And maybe, right, which is, and I think when you start having like readily available state machine libraries where, developers are familiar with them, you can all of a sudden start using very different tools to start, chopping that problem up.
Okay. So basically, if you didn't have to, so if it's complex and you get your trajectory from some planner, the previous way of doing things was you put everything in one big state, and it's all very complex to manage because you have to manage a lot of like internal variables to figure out how control should be handled.
Sure.
And so if you can chop up the state into small, clearly defined problems, then you can handle them very well because you can only consider what you need and have the you basically only have the problem parts that are required to solve the problem for that one problem rather than everything kind of mushed together. Yep. Okay.
And that also has interesting effects, back to the client libraries and stuff like this. I think that one of the ways that I hope that SMACC will influence ROS in general is that it will bring down the size of the servers and make them more manageable. So to give a little context.
What do you mean servers?
Sure. So let's look at MoveIt and Nav2. So I'm going to throw out some statistics. I don't know exactly how accurate they are. I'm sure there's people with more accurate numbers. But I remember speaking to Mike Lautman at Picnic, and him sharing with me that the MoveIt code base was something like over 100,000 lines of code. Right?
Yeah, it's huge.
It's huge. And I have a tool that attempts to tell me how many lines of code are in something, and I ran it on Nav2, and it came back at 111,000. Okay, so that sort of shows like a level of complexity in here, and some of these like extremely complex planners, right?
I see what you're saying.
Yeah.
So because you can divide things up, they don't have to get so large.
That's one. Yeah.
Is that okay?
Much simpler planners, exactly, and that's also important too, in that from our own experience of developing examples, the place that we really you just start burning developer hours is fiddling with these settings on these black box planners and checking them out during runtime and simulation. There's just a slowness to it. And the way that everybody is generally interacting with these is, okay, so you write your own node, right? Your own, which is essentially like a client that's going to interact with Nav2, let's say.
Hmm.
And I don't know, what would you say that they start at 60 lines of code, maybe 200, and then we start building out your application, maybe it's like 1,000, at some point. Um, so
You're saying 1,000 lines of code, and relative to
this
all of Nav
100,
2,
yeah,
or
yeah, exactly. You
okay,
got this small thing interacting with this massive, it's like we've put all the complexity over in these giant servers. Um, right now,
and just by server you mean code base, effectively. So
yes,
like we're referencing it as a dependency in our code, and a lot of logic is being done over there in
yeah,
their code. The thing
right.
you're okay.
Yep, that's exactly right. Um, currently, so we finished up some of the work on our Nav2Z client today. So this is the client in SMACC2 that we use to interact with navigation. And it's coming in at about 7,500 lines of code. And this is all written by, this is written by Pablo, but Pablo is an expert in navigation, you know?
Hmm.
Um, and so I'm imagining a world where if SMACC becomes a standard, right, and these clients become a standard, you end up interacting like that balance between, let's say, 1,000 lines of code in the application and 110,000 in something like Nav2 rebalances to something like 10 to 12,000 lines of code in a client. And then my hope would be that, let's say, Nav2 could come down to 70,000 lines of code, 65,000, something
What do
that
you get by using less lines of code? I'm sure storage and compile time and things, but
well,
what are
there's
kind
that,
of the
yeah, there's those.
explicit benefits?
Well, there's those, and those add up. If you figure,
Oh, compile time, yeah,
yeah,
really.
right,
Test time.
yeah.
Hmm.
Um, I do agree that measuring this in lines of code, it's a crude metric. Um, but I think what you can get is, uh, I think it would be easier for the developer teams at places like Nav2 and Move It to, if they knew that the users were going to interact with their system in like a defined way, defined by like these clients, right? If half of the ROS community interacted with Move It to through a SMACC client, right? It would sort of like narrow the
Their
interface.
focus.
Yeah, exactly.
Yeah.
And you basically get more like focus, less code, easier to maintain, um, and then also the simplicity. You'd have more planners, simpler planners that would be easier in that sense.
Yeah, and one advantage to that I see is, say you want something to be like space certified or some high level of security, or you basically the code is really hardened for safety critical
Mm-hmm.
situations. You can certify only a small chunk of a larger library
Mm.
rather than the rest of the library. So, like, I'm sure certifying 10,000 lines is a lot easier than 100,000 lines,
Yeah, yeah, that's right.
this kind of thing.
Yeah.
Let's see. And so one of the things we were saying before we started this interview was you see the application of SMACC really being for industry
Hmm.
users,
Hmm.
and as opposed to like hobbyists or this kind of thing. Can you speak on this a little bit?
Yeah,
And maybe I've
yeah.
gotten that wrong, but
No, I
mhm.
think, well, I think it's true. It's, I mean, I hope that SMACC is used by beginning developers, and I think it has a lot to offer, beginning developers. But but I don't want to like shy away from the question that when it comes to design decisions, that are going to be made, and let's say the design decision comes down to a choice between making it more friendly for, new developers, or, being able to meet one day a safety certification or something like this, I always side with the more high-end side. It's more important to me that SMACC runs on the most important robotic systems of our era than it is, I'm not counting every developer that uses it. Um,
Hmm.
where though that goes, back to the bifurcation though that I'm seeing in ROS, especially as I look down the road, is seems to me that we have on one hand like a research community, and this is like students, graduate students, people who are more focused on usability and getting up very quickly. I think they tend to be more focused on their algorithms. And so, this would be somebody who's using like a Python node or something. They want to get their system up and running quickly. On the other side, you've got those like SMACC that are more focused on actually running in production. I think also the work with self-driving cars has really led the way here. And when I look to like for inspiration and where I want to go next with SMACC, I look at AutoWare, I look at the work coming out of Apex AI. I mean, it's beautiful.
Yeah, absolutely.
But it has some interesting features to it. And we've done this with our own library. We brought in a more complex continuous integration system. And, with that, I think we have something like seven checks that we go through on every pull request. Every check we add it's just one more step that a new developer would have to go through to submit a pull request.
And so these might be like run the tests, might be like do a linter check to make sure the code is formatted right. Like, so you're saying,
yeah, exactly. Like, and hopefully automation can help lower that burden. But I think too, as the libraries like this grow more complex, it's a tough environment for beginners. It really does favor the more seasoned, focused. I don't want to say professional, but I want to say focused. Where you're focused on a certain problem set and not kind of coming in quickly wanting to get something up fast. I recently there's a library, I won't mention it specifically, but there's a library out there that I admire very, very much. And in researching it, I was going through their documentation and I found a couple of like very minor errors. The guy's English is probably their second language, and so there, a few minor grammatical changes. So I opened a pull request to change it, and it was a 20-step process through, this pull request, and I quit after like step 6. I had other things to do, and I pulled out of it. I'll continue it, but I think it just sort of highlights something that we're going to have to deal with as a community. And I see this sort of bifurcation between these two different camps.
So one thing that I find interesting is like in the web developing community, you have really high quality, difficult, give you everything to play with libraries. Like I think it's D3.js. D3. It's a chart making library. It's data driven. It's really nice.
Beautiful.
Yeah, amazing. But so that one is incredibly difficult to get into as a beginner. Like I played around with it a little bit. It's awesome. You can do great things, but they're very time consuming to do, but you can control everything. Whereas then there are, I don't know, maybe like Chart.js or something that use D3, but they make it a bit easier for users that are more casual or just want to get something working quicker to play around with it. Or to do something, but they don't have access to all the knobs and all the customization without going into D3.js. Do you imagine some sort of similar? Yeah. Okay. Well, I wanted to make sure I'm saying the right name of something. But yeah. So I mean, it's wonderful, but just it's lower in difficulty than D3. Do you imagine SMACC following some sort of model similar to this to make it more beginner friendly?
Yeah, this is the dynamics I see at play there. I think that the advantage that SMACC has is that SMACC, as your application grows, SMACC can handle it. And so what that allows for is the creation of these client libraries that are developed by experts, but basically encapsulate much of the higher level function. And note, you couldn't, or you would be foolish. So let's just say we're taking navigation as an example, right? I think you would be foolish to write a client like Nav2Z for a state machine library that couldn't handle, if it got to a certain level of complexity and then that state machine library couldn't handle it anymore, you'd be foolish to write a client for it. But because SMACC can handle almost anything that you would throw at it in terms of state machine complexity, it opens the door now for specialist developers to write client libraries. That's my number one goal as we move into 2022, is to expand the library horizontally with new clients and new client developers. And in that sense, I think that's one way that we can kind of escape this trap. You know what I mean? This D3, you know, where it's like always, you know, if you go for if you get with capability, you can't use it. You know, like avoiding that dilemma. And then the second part of that is code generation. I think when we start getting code generation capabilities that are graphical, it offers
easy,
a way to bypass all that.
You can just like visual block program a complex robotics application that actually does something, which is nuts.
Yep.
That will be super cool.
Right. And in there, you know, then the complexity, it wouldn't hurt you there either. Or you'd bypass it. You'd be able to kind of abstract it away.
Yep. In the blocks you use. Yeah.
Yeah. And that also has another, like, it brings in another type of efficiency where it's important. So the SM reference library, you know, the minute a developer comes, they can get started with the state machine there that's guaranteed to compile and run. Simulation is set up. But I think the other way to capture greater efficiency is on the back end, where you don't have to upgrade. You know, for instance, back to that DARPA team we were discussing earlier, that started off with 4 states. Their state machine eventually grew to 15. Now, let's just say it kept going, you know, and now they're at 45, and it's not working anymore. You know, like the things that they were dealing with, probably they don't, who knows how they're visualizing it, you know?
Yeah.
But if you're in a library like SMACC that you know can handle that growth, well, then you never have to refactor or transfer your code base. And that's a big, you know, that's another like form of efficiency that I'm hoping that we can provide.
You have that foresight and you can see, oh, eventually we're going to need it. Yeah, I've seen there's several things that I've seen that are similar where they're like, you're going to need to use this, so might as well use it anyway, kind of thing. Like, might as well use it to start.
Yep.
Gotcha.
Build it into your architecture. Yeah.
Huh. Now, I know, so we are running out of time. We were booked for 2 hours. We're coming up on the end. Are you okay to go a little bit longer?
Yeah, let's do it.
Okay. So one thing that I want to... So SMACC is basically for control, high-level control of robotics applications. How does it compare to other control patterns, such as like behavior trees and I don't know, what other things exist?
I think with behavior trees, you know, well, I guess the key question there is, what do you mean by exist? If we're talking about
or patterns that developers use now for control of robots that are doing reasonably complex applications,
you know,
like control in existing applications.
Yeah, you know, I'll be honest in that there really isn't much available. It's hard to comment on it, you know, because there's, and I think this is one of the real, this is a problem for us as a community at the moment, is that then the answer is we need more demos with links to the source code, you know, because I think a lot of it sort of reminds me in the days, you know, for those listening off camera, Audrow and I, before that, we're talking a little bit about, we both have an interest in jiu-jitsu. And it reminds me in the moment of like the days before the first UFC, where, you know, what would happen when a kickboxer fought a sumo wrestler? Like no one really knew, you know? And and so I feel like the demos with links to the source code are a crucial part of showing like, okay, well, you know, if it can do it, let's prove it. And from what I've seen, you know, of what's out there, it seems like most people are rolling with like a roll your own solution. You know, they're starting off with like I don't know, maybe a state pattern or something like a gang of four kind of pattern. And it's good, although I think it leads us to this sort of thing where they develop something that's pretty cool. Let's say it's 15, 20 states, and then but they can't maintain it. And so a lot of
Hmm.
that work is lost, you know? Um,
Yeah, nothing generalizes. Like it's hard to pull components from it. It's hard to grow the application any
exactly,
larger. And it's
exactly.
also intertwined with the state representation that they have already, that it's
Mhm.
very hard to pull out the parts into a different way of organizing them, perhaps.
Yeah, yeah. And I think that hurts us all over the place, where, I mean, for instance, and I know we're trying to harvest what's coming out of the DARPA Subterranean Challenge, but I think we'll be lucky if we get a couple of planners.
Hmm.
We'll be lucky if we get a few algorithms. But I think the prospects of us finding like some type of state machine architecture that we can pull out, I mean,
Very low.
very low. It would require an advanced team. I'm going to
Hmm.
adjust my lighting here a little bit. The
Sure. Yeah.
sun's going down. One moment. How's this? Is that better?
Very bright. Yeah.
Yeah. Okay. Cool. Um,
So,
yeah.
and then, so just, can you speak a little bit about the differences between state machines and a state or a behavior tree based approach, just kind of at a high level? Because,
High level. Yeah. The I think the most fundamental differences between the one-way and two-way path of control. So, and in that sense, state machines are, I guess, more like a go-to statement, although I have problems with that analogy. Whereas behavior trees are more like a while loop. When you look at a behavior tree and it's the
and,
ticking that
yep,
is like the key part that makes it a while loop, right? That you tick through all the
because you
sequences.
keep polling the current state or something too. So
Exactly.
just to give a little background to those who don't know, for the behavior tree, just an example of what it might look like is in a video game. I think I read on your blog, the SMACC one, that Halo 2 was the first video game
Yeah,
to
that's right.
control.
2004. Yep.
Yep. So what they would do, an example of how a character might be controlled in a state machine. So in Halo 2, for example, if you had like one of those little grunt aliens, it might, if it doesn't see you, it might just be kind of idle. Or actually, let's see. Actually, another example, because I'm going to get confused with that one. I'm kind of
Sure.
going into a state machine direction. If I have a character and it wants to get into a house, for a behavior tree, the behavior tree might go and look to see if the door is open. And if the door is not open, then it might go see if it has keys.
Mhm.
And if it has keys, then it might use them. And if not, it will go and see if someone, like, try to knock. And it
Mhm.
progressively goes through these things. Eventually, it might be like, is there a window that can be broken to get inside? Or something. But it's a series of like steps that are all like conditioned on each other. Do you agree with
Yeah,
that or
I
anything to
agree.
add?
I agree with
Okay.
that conditional approach. To
And
add,
and
I yeah,
the polling part is that at each time you go, what have I tried before? And it kind of brings you down each of the leaves for this. And that would be like, have I tried keys? Have I tried this? Have I tried that? Okay, I'm here. What do I try next? This
hmm
kind of thing.
there's that, and and then there's no events. And I think that's now this is true for behaviortrees.cpp and a number of other behavior tree libraries. I think
So there's no events. That means it's hard to have an event trigger something in the behavior.
that's right.
So it's kind of weird because it's based on like an existence of the state. Oh, I see why that gets confusing.
hmm
Um,
And you
because if
can't.
you're running through your statements, but then all of a sudden the state changes, now you have to like repoll everything.
That's right.
Um,
That's right. And that's if you have, that's when you start to have, so in a normal behavior, how do I say this? We'll go a little, so behavior trees originally came out in 2004. And they got started in games modeling. They call them NPCs, non-player characters, which I have a number of problems with in a robotic context. I mean, these creatures don't have any kind of control system. They don't have any kind of orthogonality. There's no liability, for. Then those, I'm going to call that the first generation implementations. They did get some success in the gaming world. And so, and I think for that reason, people thought, okay, well, we can use them from robotics, because robotics has always been, we've always stolen from every other field out there, right? But later, well, as of today, right, there are no behavior. I'm 99% sure that there are no pure behavior tree implementations left in the gaming world. And those that remain have all moved over to event-driven behavior tree models.
Oh,
and with an event-driven behavior tree, what you need is you need another thread. You need like an observer thread, to check your events coming in, amongst other changes.
So does it? Just from like a high level to see if I understand, so you have the two threads, you have the one checking for events. Would it so an event occurs, something has changed. Now your state diagram or your behavior tree, would it just like change all of a sudden?
Good question. This would depend on the implementation. I know of two different methods. One of them is like, you just repull everything in the tree every time an event occurs. And that's like, that keeps it more similar to the original behavior tree design, I guess. And then there's a second model where you're keeping track of all, it's a more advanced method where you're keeping track of everything that's happened. And at that point, I think you've actually got a state machine, only you're keeping track of state in a
second
kind of funky way. The thing about event-driven behavior tree libraries is that I think they're highly experimental. I mean, there's only 4 that I'm aware of. You got Unreal Engine, you've got one for Unity called NP Behave, and that's like a third-party plugin or something. I don't, you might catch
whatever
me
it
out.
is. Okay.
Yeah, it's like a plugin type deal. Then you've got the Cry engine, which I don't know that much about, and one other one that doesn't count either. It's not important. The only one of those that matter in any sort of way to me is Unreal Engine 4. And the big difference there is that they cannot handle concurrency. You cannot. And if we look at, let's say, the implementation of Unreal Engine 4, right? The only event-driven behavior tree library that I can think of, they don't support multiple orthogonals. And in fact, if somebody cares to look into it, in the documentation, you can look up the simple parallel node, where this would have been the node where they would have handled in their parallel nodes. You could have multiple orthogonals. They punted. You're only allowed to have one asynchronous one and one synchronous, and that's it. So you would never be able to run like the kind of orthogonality that that would be required on that field work robotics robot that we saw, or let's say some type of like military submarine, where who knows what they're gonna, or like an Apache helicopter where there's something like 48 sensor systems, and complex sensor systems, right? Not just like a proximity sensor, right? But instead it's like a 3D scanning array and a IR scanning array. And so to me, that's the main difficulty. Now there will be a lot of debate. I've been involved with debates with the proponents of behavior trees, but that to me is the most immediate shortcoming they have. I also suspect that there would be a way to prove mathematically that One, state machines are more, well, I know that you could prove mathematically that state machines are more expressive simply because the n times n problem is the flip side of that is that you have finer grained control. You know, for instance, let's say I've got a 200 state machine, and at state 199,
you can explicitly go from each of the states to every other state.
Exactly. Handling like certain corner cases. So in that sense, I think the idea that you get more exquisite,
probably way better for testing. I imagine it's much easier to test all the state transitions explicitly with this kind of representation.
I would think so. I would think so. Yeah, the fact that you can do a lot of it at compile time, I think that's true.
And even like if I want to simulate the robot for like additional testing, so like I know you can do a lot of the compile time testing, which makes sure everything has a connection to everything, or so all the connections are set up. But having like, if I wanted to run in simulation, I could target each of the transitions for a candidate for testing, which would be nice and explicit.
Yep. And then too, with this gets off into like where I see the future going, but so in studying the history of state machines in different domains, I've studied them in the electronics domain, I'll call it computing. I've been able to track down the earliest state machine in a computer to the 1965 version of the IBM OS 360. It was the first one that I was able to find in documentation where you see a very simple state machine inside the computer. But in the networking domain, you see state machines arising from almost the beginnings of the field of protocol engineering. And TCP/IP is a giant state machine. But one of the things that happened in the late 70s was they started creating like dual state machine setups where one state machine would test the protocol of another state machine, totally automated. And there were cases in the development of ARPANET where this technique exposed something like 256 bugs without any human involvement.
Crazy.
And that has got me thinking about like, okay, wait a minute. How do we start creating, or how do we start changing our automated testing, right? To start incorporating state machines on each side, testing the other state machine. This is one of those areas where I have hopes for new fields to arise and new types of efficiencies to be gained. But back to the behavior trees, I think at the application layer, I'm yet to see an example of behavior trees where we've got a demo and the source code side by side in robotics. So that
you can evaluate.
Yeah, that makes it hard to comment on. And I don't know. I feel that they're trying to deal with that problem of complexity in a sense by saying, well, you don't even need state machines. And I have a hard time going down that road. That said, I do want to say that I believe in freedom, and although I may disagree with something, hey, I want people to be able to code the way they want to code, and let the best man win. Let the best man win. Let's going back to our discussions about jiu-jitsu. I was listening to an interview with Rickson Gracie the other day, and he was asked to compare the cultures of Japan, where jiu-jitsu originated, in Brazil. And what he said was that, Gracie jiu-jitsu could only have originated in Brazil because the difference in cultures, where in Brazil there was not this sense of respect that there was in Japan. In Japan it's like, you're very respectful, right? Okay. In Brazil, he said, no, like people would show up at my father's studio in the middle of the night and want to test us out with a fight.
Wow.
Yeah, it was like you had to be ready to duke it out at any moment. And I think we need a little bit more of that in Ross. Let's put the players on the field. Let's let them run and let the best.
You can evaluate, definitely.
Yeah, I think the community benefits.
Yes, yeah, because you get to evaluate the ideas and actually compare them fairly, and then choose from there. So going forward, what's the future of SMACC look like? Where are you guys going with your implementation, and what do you see in the next few years?
I see a few years, I don't look that far down the road. I'm more like looking down
One
at the
year.
first 2 quarters of 2022 and
Okay.
that year. Um, I think there's really two things that we need to do. The first thing I need to do is I need to expand it into more of a community project. And one of the things I'm looking for there is a talented pedagogue, because I'm not the guy to teach newbies about SMACC. I'm, I'm going to try. I'm going to do my best, but I know that there would be somebody out there who's better than me at doing it. And that, I think, is probably the biggest weak point of the library at the moment,
Hmm.
partly because of the way we've bootstrapped it. But we could use a lot more documentation. We could use a lot more tutorials, and fostering it almost into more of a community beyond just the Robosoft team, which is where we're at currently, I would say. We've got a handful of people who've committed pull requests, but it's a handful. And
Hmm.
and for what I want to accomplish with the library, that needs to grow substantially. And then the second thing is the horizontal growth, and that's basically new clients. So clients for legged robots, clients
Hmm.
for naval. PX4 is another one that's like really high on my list.
That's
Um,
the drone community, correct?
drones, but you could also use PX4 based systems for like underwater subs, stuff like that.
Oh,
Um,
so cool.
yeah, um, I want an AutoWare client. I really think that would be
That'd
really
be very
awesome.
cool. Hell
Yeah,
yeah.
opens up a lot of possibilities, particularly for multi-stage missions like we were talking about earlier. Um,
Hmm.
other ones, let's see. There's the MOOS system for naval. Um, I don't know what you'd call it, but basically naval robotics.
Hmm.
And let's see, what else? I would say that that's basically it, though. The idea of
Where
horizontal
you're going.
integration. Yep, and
Yes.
horizontal growth.
And then wrapping up, what advice do you have for someone who is just getting into robotics?
Hmm. You know, I'm very hesitant to give advice to anybody. I'm not sure they'd want to do things the way I've done. It hasn't been exactly the smoothest road, but I would say this: if someone looked at my career, that they would find, and a lot of this hasn't been public because it was with the reel, um, but over and over, I've gone into development projects that I really had no business succeeding in. It would, like, if you look before, like, huh, what would this guy's odds of success be? You'd think they were low. And over I've come out of them on top. And there's one secret, and that is have a spec. Not even have a good one, just have one. uh, I originally
What do you
got
mean a
that from
spec?
Jules' book. Spec, I'm talking about a design document, minimum 3 pages, but it can grow, you know but it's where, write it down, particularly if other
Hmm.
developers are going to get involved. It's just, you'd be surprised. I've ran into people whose credentials were they looked so good, and but they didn't write a spec, and no, their code wasn't that good.
Gotcha.
But when you have one, you'll notice, that no, like, even again, you may not have that much experience, but armed with a spec, you should believe in yourself.
Gotcha. So you basically you think it through and you develop some sort of spec sheet. And with that, you're a lot more focused and able to kind of knock down the task to achieve something rather than not being focused through
Yep.
and trying to, I don't know, you're not focused on the end if you don't have a spec maybe.
Yeah, I think too, it allowed me to identify difficult problems, and often there were multiple ones, like
Hmm.
in something, and overcome them, and start to
Gotcha.
like you start to get your grips on a problem. You start to come up with solutions, often that don't work, but
Hmm.
But yeah, and I've noticed it more and more that when if I'm working with something, I say, well, do you have a spec? And it's rare. It's rare.
Mm.
But and that I originally got that idea from the book Joel on Software, and that's from Joel Spolsky, who was one of the original Microsoft program managers at a time when Microsoft really led the way in terms of how to produce code. And so that's really the one piece of advice I would give. I don't know if it'll be enough to accomplish, what someone would want to, they might first, you got to have a goal, and I don't know if a spec alone will get you there, but without one, you're done.
Awesome. Okay. Now, do you have any links or contact info or anything that you would like to share?
Yeah. So Robosoft AI is our website, and then the other place that for especially the audience of this podcast is the SMACC2 repo on GitHub, and that's always the most updated source of or up-to-date source of information regarding the repo. And I guess the last thing out there is if you're a developer and you've got an idea for a client or like a SMACC client that you want to develop, something like nav2 or we have nav2 and Move It and ROS2 Control, but if it's something like PX4 or Moose or AutoWare, get in touch with us. We will support you, and we want to hear from you. I'm looking for artists globally.
Awesome.
Cool.
All right. Thank you. I've enjoyed this.
Thank you very much, Audrow. I really had a great time, and it's an honor to be interviewed. For those just tuning into this podcast, I'm telling you, this guy is the Charlie Rose of robotics.
All right. Thank you.
Thank you.
All right. Bye, everyone.
Bye.
Thanks for listening to this conversation with Brett Aldrich. Thank you again to our founding sponsor, Open Robotics, and I hope to see you next time.